calculators back here. Is anybody missing a calculator? One has green in the back. One has a sheet and then writing on the top that I can't read. And then one has writing in the front that I can't read. They're nice calculators. Huh. No, but you're allowed to use your calculator. No solving by hand in this puppy. Look at those decimal answers. Does that make sense? Holy cow, the air turned on and there's very few of us to absorb their coolness. Whew. Hi, seniors. Juniors are working on... yeah, Haley.
Yes.
Juniors are working on an AP practice problem like section 6.2a. Volumes by cross sections, which are technically the end of your homework. I just said hi to you on the video. Oh, now I'll say hi to you in real life. That's weird. I was talking to your future self.
Oh, sounds good. Are we allowed to sit there?
Yeah.
Okay.
Opening up your guys' math book real fast. Now, the nice thing is with this one, kiddos, let me go ahead and pull it up on our actual notes. Except I just lost my stylus yet again.
This one over here? No, I know. It's over.
Alright, is it on screen? Oh, it's still on screen. Ay, mamma mia's. Alright, why were you guys supposed to be able to visualize the graph even though it's a graphing calculator problem?
It's a forever card.
It's a forever card. They're basic graphs, right? So we're dealing with ln, the line x equals e, and the x-axis. So, what have we figured out so far? Okay, and why is that? What's the key phrase that tells you that? Okay. Perpendicular to the x-axis, that's important. Region enclosed by ln, e, and the x-axis, that's important. And then squares, isn't that important also? Okay. And we're talking about volume. So if we were to, can I kind of be a little bit three-dimensional? If we were to draw this graph, here's my x, here's my y. X equals e, can anyone tell me a quick approximation for that?
2.2.
Yeah, so we can say 2 point something, something, something if we want. We could put like a 1-ish, we could put a 2-ish, and then there's like a 3-ish. It's 2.78. 71828, is that right? There's e. So we can say that line's kind of important. What other line's kind of important? That's an awkward line, by the way. It's not very parallel. My artistic ones, I apologize for. That's not much better. Okay, the x-axis, okay, so it's bounded by that, and then ln. Where does ln go through the x-axis? Yeah. So ln we could go ahead and show is something like, true? Alright. Enclosed by. Do you guys see what region they're talking about? Enclosed by the x-axis, x equals e, and then the curve. Okay. So we're talking about that region right there. Thinking about there are 3 parameters. What's in between ln, e, and then the x-axis. And then they say perpendicular to the x-axis, which is what Katrina pointed out. Sorry, Katrina Ortega walked in this morning. I'm distracted. Popping up in squares. Now, you don't have to draw this beautifully. You don't even technically need to draw it at all. But what you do need to know is, if it's perpendicular to the x-axis, what's my thickness? Dx. So I need everything in terms of dx. Now guys, the shape itself, there'd be lots of these slices, right? So you'd have like ones up here, that it would be 3-dimensional. You'd have ones in the middle, that would be 3-dimensional. You'd have little itty bitty ones that are 3-dimensional, right? And the whole shape would be the accumulation. It'd be kind of like one of these rounded thingamabobs. But we don't have to necessarily go into all that detail. What we need to do instead, just think about one. So you can get rid of all the extra stuff I drew. Okay. How do I find volume using cross sections? What's my formula? x1 to x2, which we'll fill in a second. Then we need an area formula, dx, right? Okay. So what's the area formula for a square? Okay, so we're going to do s squared. What's my s equal according to my picture? Yeah, because see, can't we look at this side down here? And that side down there, we could say, oh, hey, s is equal to top minus bottom. And who's on top? Good. And who's on bottom? Y equals 0. Does that make sense? The x-axis. So we can say y equals ln of x. That's one curve. But we can also say y equals 0 is the other function that's cutting this off. Does that make sense, kind of? So the bottom, top minus bottom, I have ln of x minus 0, which does end up just being ln of x. If that's my side, then I just need to plug into my volume formula and say, oh, side, ln of x, squared, got it, dx. And we'll come back to what you guys said were my bounds. What are my bounds? Yep, so we're going from 1 to this cutoff point, which would be e. So we're going to throw that in from 1 to e. Now, if you plug and chug that to your calculator, what would you get? Did anybody get there before me and plug and chug it? So letter A. Did you guys make sure to put the little squares around the integral? Or sorry, around the ln of x when you integrated? Do you guys notice that in alpha y equals, underneath function, there's a little function integrate? We've talked about that shortcut before, right? You don't actually have to go all the way into all the messiness. I'm just double checking. I trust you all. Just making sure. And final answer is, got it. Okay, you guys ready for another one? Yeah. Any questions on this one before we move on? Yeah.
How could you recognize that without drawing it?
You could see perpendicular to, like, let's just say I zoom in on this for a bit. This is how you could read it. Perpendicular to the x-axis are squares. I know that I'm going to need something squared, and I know I'm going to need a dx. When they tell me x equals e, I know somehow it's going to be one of my bounds, right? But how do you know the other bound? You could say ln of x equals 0. Remember, you could find the intersections. So then we could do e to the both sides. X is equal to e to the 0 is 1. So I know 1 is going to be a bound. I know e is going to be a bound from down here. So we can say which one's lower, 1, which one's higher, e. And then we could do top minus bottom. Since we know it's a cross section, it's some sort of area between some sort of curve. So when the shape, I shouldn't use that marker. When the shape, which is a square, pops up, the top minus bottom is going to be the actual side of the square. You kind of make that deduction. And then if you think about it, if we're going to square it anyway, does it really matter whether I know the top or the bottom? Yeah. So that's how I can kind of do it without even, like I could do 0 minus ln of x and just like do 1 minus the other. But in this one, I definitely think that being able to at least get this yellow region down here helps a lot, and then just think I'm popping up in a square. I think the visualization helps a lot, but it is kind of possible, almost always, without a picture as well. Okay. Kiddos, how is this one different? Nice thing is I figured not many of you would know what this graph looked like, so I went ahead and already plugged it in and gave you a picture of the graph. This is a calculator problem because there are these little decimals up here. So we know it's going to be a calculator problem. Oh, and it says calculator permitted. So it shows you what the graphing calculator gives you, but I'm going to give you just, I don't know, like a minute or two to be able to read through it and think about what's going on. To read through it and think about what's going on. Sounds a little different than 6.2a. Something is a little new. But what is it? Josh is twirling his hand. Why is he twirling? Jason is also. Revolving. What did we do last year with revolving? Conic sections. Didn't we figure out how to make little paraboloids, and then we would say, hey, let's rotate it about its axis of symmetry. Remember that? And then we show our little spin, 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 and we're like, hey, when you rotate a parabola, what do you get? A paraboloid. If you rotate a hyperbola around its conjugate axis. Around its conjugate axis, you get a hyperboloid that's only made from one piece of material, aka it's called a one-sheet hyperboloid. We rotated things last year. We rotated them around axes, and when we rotated them, we took some original shape that we had, and we said, hey, let's spin it, aka, let's spin it. Let's make circles to show that rotation. We could be really cool with it if we really wanted to, yada, yada, yada. But we were spinning stuff. Now my question is, with calculus, question, if you were to slice this, what shape would its cross sections have? Does that make sense? And not just any circle, we're going to actually call this a disc. Because we're assuming that this hyperboloid is not just hollow, but instead that it's actually solid. That's not just hollow, that it's solid. Now, hold on. We're not rotating a hyperbola. What are we rotating in, or revolving in this picture? Yeah, kind of like half a parabola. That's what it sort of looks like. What are we revolving it about? This will make a huge difference. The x-axis. So show your little rotation arrow like we did last year. The little rotation arrow is basically like a circle with an arrow at the bottom half or the top half. You could rotate up or rotate down. When we rotate, this circle needs to be seen in the figure itself, if you were to actually show this. This circle needs to be seen in the figure itself. I'm going to go ahead and show it this way, so the third dimension would be coming out like this. No, that's not right. It would be going back like that. Anyway, I'm going to make it so you can actually see the third dimension. This region is rotating. Okay. What region? How was I able to know it was only that portion? What did it say, cool kids? Bounded by the graph, the x-axis, and the y-axis. What's in between the graph, the x-axis, and the y-axis? This region is what's being rotated, and that's a solid region. So when we rotate that region around, we get that three-dimensional object with this said volume. What volume? I don't know, we have to find it. We'll stink. How do we find it? Think about a slice. Let me pick a dark color just so we can see it a little bit more clearly. How about like green? I showed you in the hyperboloid a second ago. Think about a slice. If we were to slice it, right? We'd have this right here. We'd have a disc. It would technically not be smooth. It would kind of be jutting out because it would be an approximate. My question to you is, would this be a dx or a dy? If you think about it, your rotation arrow, if you were to make that have a third dimension, wouldn't that be a dx also? That's kind of a good way of double checking. If you're revolving around a horizontal line, the thickness or the depth is always going to be dx. If you're revolving around a vertical line, the thickness is always going to be dy. If we were to use our formula from section 6.2a, we would say volume is equal to the integral of a of x dx. Stink. What would our bounds, well, we'll figure it out in a second. From one x to another x. Question, what's our area formula if our cross sections are circles? Good. Pi r squared. Let's look at our picture. What would our bounds be? 0, because that x equals 0 is the beginning of the shape, right? When does the shape end? Uh-oh, what x is that? Yeah, it's hard to count the tick marks, and if you guys are already pretty sure you know what it is, how can we solve for it though? Yeah, can't we set 0 equal to the function, which would be 8 minus x to the 3 halves? Add x to the 3 halves. Raise both sides to the 2/3. to get rid of our powers. Some of you might not remember how 2/3 works. Remember the third is a cubed root and the 2 is a da-da-da. Or you can also think about 8 as 2 cubed to the power of 2/3, in which case the 3 is reduced, 2 squared is going to be 4. That's one way. You could also take 64 and then cube root it. Cube root of 64 is also 4. But either way, we get our upper bound to be 4. So we can say there we go, I was trying to move that over. Volume is equal to the integral from 0 to 4 of pi somebody squared. Now wait a minute, who's our radius according to our picture? With cross sections, it was top minus bottom divided by 2. Who's the radius in this guy?
Top to x-axis.
Wait,
Yeah.
So just the reason.
But the nice thing is, see that the shaded area, the yellow behind, doesn't the yellow determine the radius now? I don't have to cut it in half. I can just do top bottom. Not of the whole figure, but of the shaded region below. So we're going to do top minus bottom in order to get our radius. So we can say r is equal to top minus bottom, which is going to end up being 8 minus x to the 3/2 minus 0. Our function, 8 minus x to the 3/2 minus 0. So we can say, sweet, let's plug it in. Anything minus 0 is itself, so we'll just say 8 minus x to the 3/2 squared. Now, of course, kiddos, they would pull this pi out, because they're like pi is a constant, so they pull that pi back. I don't know why I just said 8. It's supposed to be v. V is equal to, we'd pull that pi out, we'd have 0 to 4. 8 minus x to the 3/2 squared dx. Sometimes in multiple choice answers, they just have the expression for the volume. However, if you were to go ahead and solve this, you're using your calculator, so the pi is going to be absolved in. Just don't forget to multiply by pi. Do pi times first. Pi times the integral from 0 to 4 of, don't forget your squared, 8 minus x to the 3/2. The entire quantity squared dx. I'm solving it, you guys solve it too, and our final answer is, yep, I got it too, 361.9. Ella.
so if this were a multi-answer, could we leave it at b equals pi? 0 to 4?
Only if they said give the expression but do not solve, or state the integral that would be used to solve. They almost always say do not solve if it's okay to end. In a multiple choice, you just kind of look, but they probably have also said do not solve in there. Good question. So what was new in this picture that wasn't in the picture? That wasn't in the picture before. Where was the area between curves in this picture when we had cross-sectional slices? Was the area between, was it generating the 3-dimension, or was it just the base of the 3-dimension? It was just the base. It was just setting the parameters for the cross-sectional slices that were being formed. It just set the parameters. But in this figure, what did that area between actually do when you revolved it? It generated, or it made, the 3-dimensional figure. So the difference between the cross-sectional slices and the volumes of solids of revolution, cross-sectional slices, the area between the curves is just the base region, and you have these cross-sectional slices popping up out of this base region, which is the area between the curves. In solids of revolution, the base region itself, or I should say the area between curves region, is what actually makes the 3-dimensional object when it's revolved. That's a lot of random highlighted circles, but there we go. So this leads us into, we talk about that one tomorrow. This one leads us into the notes that you guys were taking hopefully at the beginning of class during zero period. Now technically I said you didn't have to have these totally written down until tomorrow because the seniors are going to watch this tonight and get it written down for tomorrow. So if some of you guys are like, ooh, I haven't done these notes yet, that's okay. We're going to do one more example and then I'm going to show you in your homework what you can do so far. There's a lot you can't do, but there are some things you can do. So for those of you guys that haven't taken notes, just kind of take a second and maybe not write anything else down. Those of you that have taken notes, maybe you can fill in a few things. First of all, do you guys notice for this figure that maybe you have, maybe you haven't drawn yet, and it's kind of awkwardly missing the top of this figure. It's kind of really sad. I have no idea what happened to him. Somehow he got it like erased or something. Do you realize there's an area under the curve that's below this? Do you see that? There's an area under the curve that's below this. It's actually all right here. He was what was there to begin with. Area between curves. You have this curve on top, and then where was he cut off? I think he was cut off at the x-axis, right? You have this area between curves. What was done to him? He was revolved about the x-axis, as we can tell by our rotation arrow, which is why the formula down below shows or signifies or is in terms of x, because that depth of rotating around a horizontal axis of revolution is going to be dx. After you revolve this figure, do I have a pink? I don't. Custom, where's it pink? There we go. When it's revolved around, which is what I was trying to show there. After this figure is revolved around, I do have a three-dimensional figure, and that three-dimensional figure, when sliced, gets this circular cross-section, right? And a circular cross-section has, or a circular slice, has a thickness of dx, right? Has a thickness of dx. Question. Why in the formula right below do I have pi times top minus bottom squared? Why do I have top minus bottom in there? What is it standing for? Radius. The radius of any cross-sectional slice all along the way is always going to be the length of top minus bottom. How is that different, once again, from cross-sections? Cross-sections, you would maybe have some sort of area between curves. If we had circular cross-sections, you would have a circle generated up out of that area between. You would still have a dx if it's perpendicular, like to the x-axis, etc. But what would be different in a cross-section is that your top minus your bottom would give you what measurement of that circle? Diameter. So for cross-sections, we'd have to cut that top minus bottom in half because we have circles coming up out of an area between. When we're dealing with solids of revolution, we're taking an area between and revolving it, so its top minus bottom will be the radius. And that's where you guys got this forever card from down below. And I wanted to explain these pictures that are with this forever card down below. Because there's a couple things that it might be a good idea to add to these. Bless you, bless you, bless you. Add to these figures. For instance, bless you, bless you. With these rotation arrows, if you're rotating around a vertical axis, we can say the depth is going to show us dy. Or you could think about if you were to show a representative rectangle, and that's what got revolved around. Your circular cross-section would end up having a depth of dy. So remember, if we're rotating around a vertical axis, it's going to involve a right minus left, which is what you should see in your forever card. It's going to involve a right minus left, which you should see over here. Right minus left is going to find our radius. R equals right minus left. What's different when you're rotating around any horizontal axis? Depth is going to be signified by what? Good, dx. And you're going to see that represented also when you take a representative piece and think about revolving that representative piece, making your circular cross-section. Once again, you're going to see that depth as dx, and your radius is going to be top minus bottom, which once again you should see shown over here in the formula. Real quick, AP guys love to show answers without a pi to try to confuse you because you get so focused on this that you forget there needs to be a pi. That's one way that you can make a mistake, or even in your calculator, forget to multiply by pi. They also love to leave off the squared. Now, kiddos, this is the process for finding the volume of a region that is rotated or revolves around an axis, forming a solid slice, which we call a disk. So we can call this method volume by disks. Now, the struggle is, didn't you guys have 2 pages of notes to take? The other page of notes, which we're going to do some examples tomorrow. We're going to mostly do examples tomorrow. What's different with this guy, which some of you still need to copy down tonight? There's a hollow inside. Do you see that? Something's been cut out. Think of a donut, a normal donut, not a jelly-filled one, a normal donut. Hold it up to the light, and why do you see light through it? There's a hole. Donut holes. There's a hole. That's been punched out, or maybe it's just been formed that way. But either way, there's a hollow inside. Same thing with washers. There's a hole in it. Anyway, a boot cake.
Is it a cone-shaped hole?
In this one, yes, it's a cone-shaped hole. So think about if you were to form this figure. You could use like a lathe or something in order to cut out the outer region, but you would also need to cut out something from the inside. It's not a solid piece. And you guys notice why down below I say whole minus hollow? Now, here's a struggle. Whole, some of you might think H-O-L-E. What am I referring to whole as? The whole thing. So the whole thing minus the hollow thing. So I have the whole minus the hollow. Okay? One of the most common mistakes that kids make when it comes to these types of figures is they see, do you guys see the area between curves, the green thing hidden back here? There was an original area between curves. Our way of remembering washers is the area between curves does not hit flush with or totally against the axis of revolution. Do you see how there's this gap right here? Right? There's a gap in the middle. If this area between curves does not lie completely against the axis of revolution, there's going to be a gap. And whenever there's a gap, there's going to be a hollow. Does that make sense? Okay. Whenever there's a hollow, once again, here's the most common mistake. People see that area between and they're like, oh, yay! From the first forever card, I know top minus bottom is the radius. But that's not right. That's not right. Even with my circular cross-section that's displayed here, the black and yellow thingamabob, top minus bottom is not a radius. We don't call that a radius. So here's the dealio. What we got to do is we got to say, what is the radius of the whole thing, aka down below? What would be the radius for the bigger shape? And what would be the radius for the smaller or the hollow? There are 2 different radii that we have to work with. What's the radii for the whole thing? And what's the radius for the hollow? So if I was to go ahead and try to color coordinate just so we could see in this figure, let's make, let's make the whole blue. And the whole radius would be from the very outermost all the way into the axis of revolution. It's from the very top, the uppermost, all the way down to the bottom of the axis of revolution. If it helps, you can think about your little rotation arrow. Very top to the very axis. It has to go all the way down to whatever you're revolving about. That's the whole radius. What would the hollow radius be? It can start from the same place, but it's only going to go up to the bottom. So there are 2 different radii. We have an upper radius and a lower radius. We have an outer radius and an inner radius. Does that kind of make sense? And once we separate that, we can go ahead and mathematically say, oh, we just need to set up 2 different expressions. We're going to set up 2 different expressions. We're going to go ahead and multiply pi r squared for the outer. So we can think about like up above. Pi big R squared, if that helps. Big R for the bigger R. We can also call it, if it would help, the outer radius. And then we could say minus pi little r squared, and we can call that little r the inner radius. And all of that is in context of needing to plug in pi r squareds into an integral in terms of the proper dx or dy. So top minus bottom of the outer radius, top minus bottom of the inner radius. The whole thing minus the hollow thing. Two separate pi r squareds. We cannot put them all together. And this leads us up to what you guys see down below. For a horizontal axis, I could show all that same work I did just a second ago in the sense of, hey, we can say horizontal axis, we're going to have a dx because the depth is dx, which could be seen up here. We can think of the whole the top minus the bottom of the hollow region being little r, the top minus the bottom of the whole region as being big R, just for sake of it being clearly seen from our seniors later. I'm going to put a little r, and I'm going to put a capital R. So big R is the bigger one, the outermost minus the axis. Little r is going to be the innermost minus the axis. So to make sure we do top first and then bottom. Whereas down here I could say the depth around a vertical axis is going to be dy. And I can label the whole thing, the big R, right minus left, and then the hollow, little r, right minus left. The capital R will obviously R. So, tomorrow we're going to do examples how to use this. We do have Forever Card 48, Forever Card 49. If you notice, I was saying we might stop at 49, which means we might not have another Forever Card. This is the end of our new material. But in AP Review, we might get a number 50. Some people have lost a card along the way, so they're like, no, we're good. But anyway, tomorrow we're going to do examples. Make sure you have your calculators, but we're going to go ahead and look at examples of how to find volumes when you revolve regions about axes. Now real quick, kiddos, can you tell why the bottom example that's not crossed off is a washer, whereas the upper two are discs, are not washers? What do you notice about what's in common with 1 and 3 that is not in number 2?
They're on
They completely meet the area, right? Completely meets, which I would say is flush with, is totally against. Anybody in carpentry should know this flush with. Totally against the axis of revolution. It completely meets. There is no hollow. There is no space. Same thing same thing with number 3. That area is completely against, flush with, completely against the axis of revolution. There is no hollow. But what's going on in number 2? You notice it touches somewhere, that's true. But is it flush against? No. So when you revolve, what's going to happen? It's going to have a big hollow on the inside. And the hollow technically is going to be similar to a cone. It's not going to be nice, but it's going to be similar to a cone on the inside that's kind of hollowed out, empty space. All right, kiddos. However, we're not going to have time to do those examples today, plus I really want the seniors to be here. Make sure you have these 2 pages in your notes done. Copy down to the artistic extent that you desire it. I'm going to show you in your book real quick what's going on. You guys technically have homework. Here we go for section 6.2. Here's the following. Here's the problem. All of these are solids of revolution, solids of revolution, solids of revolution. Wait, isn't that what we just have been doing? So let's check out homework real fast and let's see why I'm saying you can start the homework backwards. What do you guys notice about starting at number 70, 70, 71, 72? What do you see? Those are cross-section-y ones. So, if I were you, in keeping with us not wanting to fall behind in homework, couldn't you try the end of homework first? No, you don't like that? Couldn't you try the end of homework first? To that extent, here's what I'm going to do. You ready? If I can actually get homework to be where I can see it. Oh, little hand, thank you. No, little hand, thank you. Okay, 70, 71 are all cross-sectiony things. I also gave you guys, what, 73, 74? Oh, that's a revolving one, and that's a revolving one. Lame sauce. So here's what I'm going to do in your homework. I'm going to go ahead and I'm going to take these, which are pretty intense problems in and of themselves. I'm going to do this. I'm going to do that. I'm going to do this. And I'm going to do that. Why? Oh, that just messed everything up. Don't worry, I got this. Just you wait. Henry Higgins, just you wait. Okay. No, my fair lady. I'm going to put 70 and 71 in the beginning. So, tonight, make sure your notes are copied down. Work on 70, 71, and if you want to start playing with 3, 6, and 7, that's where we are going to be practicing tomorrow. Bye, cool kids. Thanks for all the work you did today. Friday puzzles will come tomorrow because seniors are here. Money for t-shirts, sweatshirts, and hoodies. Anyway, if you guys have it, give it to me during lunch or after school. Otherwise, tomorrow, have it for sure. It's due by tomorrow at the latest. Bye, cool kids.